The next topic is to introduce the concept of measure. So let's write the definition here. A measure we have a set S and then we have a calligraphic S that is a sigma algebra. So let's know that this is a sigma algebra on the base set S is a map which is a function from the sigma algebra to the extended real numbers from 0 up to and including infinity. And it is a function, so we kind of to every set in this sigma algebra, to every set we assign a number, which could be something non-negative or it could be infinite. And we require two properties. We require that a measure of nothing is 0, and we require that that if we have a list of elements or infinite sequence of elements which are in the sigma algebra, and if they are disjoint, so they don't overlap each other, in that case we require that the measure of the union of these sets is the same as the sum of these measures. And this property is called the second property is called countable countable additivity. In Finnish, this is called mitta, as you might know. In Swedish, mått. Right. And what is there to need to be careful? We just kind of learned what does it mean to make addition and multiplication on the extended real numbers. So note that any one of these, each member of this sum here might include something which is infinite. So we are allowing infinities now in the sum, but now it doesn't matter. We just defined what does it mean to have infinite plus something else. So we know now how to do this sum also on the extended real numbers. So everything on this equation could be also infinite, and that's included in the definition. If this is your first time when you see the definition of this, so it might sound confusing to work with the infinities, but don't worry, you get used to it. Sometimes you might just forget, okay, that I include infinities might be there. So maybe let me say that a good way to think about this, that first you ignore the infinities, you pretend that everything is finite, you work with pretending that everything was finite. That's how we usually work. And then when we have done all the computations that we did, then afterwards it would be a good habit, okay, of checking, did my computations go well if it so happened that some numbers that I was computing with, if one of them was infinite. So in the last place, it would be a good practice to check your calculation again, that the infinity didn't cause any problems. Usually it does not. Especially when we are restricted to the non-negative real line. But we need to be careful. And yeah, that's how things go. Then what else do we want to define? We want to define also the probability measure. Well, what is that? It is just a measure with total mass The total mass is the measure of the full space, and in this case, it's the mu of now the set S. Be careful with the calligraphic and non-calligraphic. So this non-calligraphic means the full set. And remember also that this full set is a member of the sigma algebra because we remember sigma algebra contains the full set by definition. So the total mass is the measure of the full set, and for probability measures, we require it to be 1. That's it. What is there? What else is there to define? Let's also call that the probability measure because it's so crucial thing. So it is also called a probability distribution. So probability measure, probability distributions, they are the same thing. It is a function from sigma algebra to turn non-negative real numbers, which is countably additive and assigns 1 as the total mass. Any questions about this definition? Okay, one remark. For some people, distribution in mathematics might mean something else. So the people who work in functional analysis and let's say, in functional analysis and in analysis on, let's say, infinite dimensional metric spaces. So distribution might mean a different thing in the sense of Laurent-Schwarz. But for us, probability distribution means the same as probability measure. That's about the definitions. Now maybe I'd like to be a bit lazy and not write everything, but instead we might open the lecture notes and see where we are in the lecture notes. And let me share this screen for you. That is here. Can you see a PDF? Thank you. We have a PDF file here. This is the lecture note, chapter 2. And as you see in the title, it is called Measures and Probability Measures. And maybe let's see if there's something to remark. So, okay, we can skip this, and the starting place is this. Okay, there's some little nomenclature, some terminology. For example, some people like to call a measurable space something where we have a pair of a set and a sigma algebra. And then subsets of the sigma algebra are called measurable sets. Okay, that's not very important. We always work with measurable sets and we want to work. So these names are maybe not so crucial. Then, okay, this was repetition from previous lectures, so we don't go there because we know how to repeat from previous lectures. They are online, the lectures, so you can play them back if you like. Then we check here in the lecture notes. Here was the definition of a measure, and that let's verify that it's consistent what we just looked at handwriting. So this is a function from the sigma algebra to the extended real line. Okay, Kalle likes to put plus here, so plus infinite to mean the positive infinity. But if I forget the plus, so you know that I mean the positive infinity anyway. And these are the two properties. So the empty set and then the countable disjoint union. So let's once more say something about disjoint. This is important. Wait. Okay, I think you know it from basic probability. The additivity works for disjoint unions, not non-disjoint. We'll get back to that soon. Then we have the definition of a probability measure here, and this is just, okay, for probability measures, we sometimes use we often think about omega and f as the set and the sigma algebra. to speak about kind of abstract probability distributions. On the other hand, we often, when we think about concrete outcomes, so then we think about S and the calligraphic S. But we can define probability measures both on kind of omega and F and S and calligraphic S. That's it. Okay, the interpretation omega, the full set, is the sure event, and something which some event which has a mass 1. So, okay, there could be other sets which have a mass 1. So let's say omega is the full set; it has a mass 1, but there could be some other set E which could also have a probability 1, and that's quite actually usual. And of course, you know it. And for such sets, we use the term almost surely. Personally, I'm not a great fan of this term. I would also like to say surely also in this case. I think this is a bit of a misnomer, but it's in the spirit of Henri Lebec, who used the term almost everywhere when he and the colleagues were developing the concept of Lebec measure theory and integration theory about 130 years ago. Okay, one more thing about terminology is that sometimes we say that the mu is a measure on S. That means that there is some sigma algebra, underlying sigma algebra that we mean, and we sometimes are lazy and we don't write it. Or we say that P is a probability measure on omega, so then we mean that omega has some sigma algebra that we think that we have fixed once and for all, but we don't want to write it down at every time. Okay. If we have a set, a sigma algebra, and a measure on the sigma algebra, so then that's called the measure space. If we have a set omega, a sigma algebra on omega, and a probability measure on this sigma algebra, then we call this triple a probability space. So these are the standard names for things. Okay, you see there are lots of names. We also say that, yes, we note that for general measure, the total mass could be infinite. So the total mass could be also infinite. It could also be 0. So total mass could be 0 as well. That's rather a trivial case, but this is possible for some measures. And we recall that the total mass of mu is the number that mu assigns to the full set S. And measures with total mass finite are called finite measures.